Welcome, welcome, deep divers. Have you ever stopped to truly appreciate the invisible powerhouses that surround us every single day?
You mean the electronics humming away inside everything?
Exactly. I'm talking about the intricate electronic circuits silently working behind the scenes, from the smartphone you're holding right now to massive, complex machinery humming away in factories.
Yeah.
These aren't just collections of wires and chips. They are like the literal backbone of our modern technological world. They operate with this hidden complexity that's really truly mind-boggling when you think about it.
It's quite remarkable, isn't it?
Yeah,
We interact with these systems constantly, but their inner workings remain a mystery to most people.
totally.
It's kind of like admiring a skyscraper without understanding the complex engineering that went into its foundation, its steel skeleton, and all the intricate plumbing and electrical systems inside.
That's a perfect analogy, and today we're pulling back that curtain. We're taking a deep dive into the fascinating world of unmanned aerial vehicles, or UAVs, drones as well, most of us know them.
Ah, drones. Good example. Seems simple, but definitely not.
Right. While they might seem like simple, intuitive devices to fly, their engineering reveals an absolute marvel of interconnected components and really sophisticated design.
Mm-hmm.
So our mission today is to demystify that entire journey. We're going to trace the entire life cycle of an electronic circuit, from the initial spark of an idea
Right, the very beginning.
through its meticulous design and the intricacies of manufacturing, all the way to its operation and ongoing maintenance.
And using drones as the lens to look through.
Exactly. We're
Yep.
using the cutting-edge world of UAVs as our guiding example.
And we've pulled together a diverse stack of sources for this deep dive. We're covering everything from the fundamental principles of circuit design and debugging techniques
The real basics.
to the highly specialized components and software that enable those advanced drone capabilities we see. So this deep dive is designed to give you a shortcut, sort of, to being well-informed about the incredible interplay of hardware and software in these complex electronic systems. All without getting too bogged down in every single technical spec, hopefully.
Okay, let's unpack this. Every single sophisticated electronic system, whether it's a drone or, something else entirely, starts long before anyone picks up a soldering iron.
Oh yeah, way before that.
It truly begins with a clear concept and a detailed set of requirements. Think of it like this. You wouldn't start building a house without a blueprint, right? And even before the blueprint, you need to know what kind of house you want and what it needs to do.
That initial conceptualization phase is, well, it's truly crucial. It defines the parameters and constraints that will shape the entire design process that follows.
Makes sense.
Without a clear understanding of the mission, every hardware and software choice you make later would just be arbitrary. It'd be like trying to build a complex machine by randomly throwing parts together. It just wouldn't work.
I can imagine. Total chaos. So let's talk about a specific example. A small UAV customized for sports aerial filming.
Okay.
Imagine trying to film an extreme sport, maybe, where a full-size helicopter would be too loud, too dangerous, or simply couldn't get close enough. This drone steps in.
Right, filling a specific niche.
And the core goal here is fascinating. To autonomously track a moving object, let's say an athlete in a high-speed mountain bike race.
Okay, the dynamic target. Tricky.
In a dynamic sporting environment, all while using an onboard video camera.
Yeah, this isn't just about flying a drone and pointing a camera somewhere. The operational challenges are incredibly significant.
Like what?
Well, you have to contend with unpredictable object movements, for one. Then there's the ever-present issue of image noise, think low-light conditions, or just shaky footage.
Yeah.
Variable illumination, like moving in and out of shadows or dealing with bright glare. And then there's a whole host of critical environmental conditions that can severely impact performance.
Yeah, the environment.
Overcoming these constraints is absolutely essential for robust, reliable object tracking.
And the environment itself throws some serious design hurdles at you. Our sources actually provide a real-world case study, which is cool. It's from the city of Cochabamba, Bolivia.
Oh, interesting. High altitude?
Exactly. Just listen to these stats that designers had to factor in.
Yeah.
An average temperature of 17 degrees Celsius, but with swings from 9 all the way up to 27 degrees Celsius.
Big range.
Average wind speed is pretty low, 3.4 kilometers, but it can max out at 12-kilometer gusts, maybe.
Okay. Manageable, but needs to be considered.
And here's the big one you mentioned. The average altitude is 2,600 meters above sea level. That's over 8,500 feet.
Wow, okay. That changes things significantly.
It means air density is reduced by a whopping 20–40% compared to sea level.
That reduced air density is a critical factor for any aerial vehicle. It directly impacts propeller efficiency and motor performance. You need significantly more power just to generate the same amount of lift.
So the motors have to work harder, propellers need to be different, maybe?
Pretty much. The drone's entire propulsion system, motors, propellers, even the battery supplying the power, must be carefully sized and optimized to compensate for these high-altitude conditions. It's a fundamental challenge that influences nearly every aspect of the design.
And beyond the climate, the scenario itself has strict conditions. We're talking mostly urban and suburban areas.
That's obstacles.
Yeah, buildings, trees, and crucially, electrical wires and towers are constantly in play as potential obstacles.
Right. Very dangerous for drones.
This dictates very specific operational limitations. Manual flights are restricted, say, up to 200 meters horizontally and 100 meters vertically.
Okay, defined boundaries.
And for safety, the drone must approach its target no closer than 10 meters away and maintain at least a 5-meter distance from any static or dynamic obstacle.
So significant safety margins built in.
This really hammers home the importance of precise navigation and control, doesn't it? It's not just flying, it's navigating a complex, cluttered, ever-changing environment.
It absolutely underscores how intertwined the conceptual mission is with the physical and environmental realities. Every single one of those parameters directly translates into a requirement for the electronic systems.
Oh, so?
Well, think about the precision needed in its sensors and control algorithms to maintain those safety distances, or the power systems needed to keep it airborne under those demanding high-altitude, potentially windy conditions. It's a delicate balance of ambition and physics.
Okay, so once you have this clear concept and all these requirements hammered out, the next step is to translate that vision into an electrical language. And that language is primarily spoken through schematics. So what exactly is a schematic? If I'm trying to picture it, what should I imagine?
Okay, so at its core, a schematic is a fundamental engineering document. Think of it as the conceptual drawing, or maybe the architectural blueprint of an electrical circuit.
The blueprint, okay.
It uses standardized graphical symbols to represent components like resistors, capacitors, transistors, all that stuff. And it precisely illustrates their interconnection.
How they're wired together.
Exactly. But critically, it does all of this without necessarily adhering to scale or physical layout. Its sole focus is on the electrical connections and the functional flow, showing how electricity travels and interacts within the circuit.
So it's not like a map of where everything physically sits on the board, but more like a diagram of how it all talks to each other electrically. I like that.
That's a great way to put it.
Our sources actually break down several types of electrical schemes based on their purpose, which is pretty insightful. It's not just one static document, apparently.
Precisely. These classifications, often found in standard engineering practices, provide a clear hierarchy of design abstraction. Think of it like looking at a project from different levels of zoom.
Okay, different zoom levels. What's the widest view?
First, you have the structural scheme. This is the highest level overview. It defines the main functional characteristics of a product, its overall purpose, and how its primary parts interact. It's like the initial block diagram showing the main systems of a car: engine, transmission, braking system.
Got it. Like, this drone has a power system, a flight control system, and a communication system. Very high level, focusing on the big block.
Exactly. Then, zooming in a bit, comes the functional scheme. This one delves a bit deeper. It elucidates specific processes and operations within those individual functional parts and the product as a whole.
Okay.
It's more detailed than a structural scheme, showing how those big blocks operate internally, but still less comprehensive than what comes next.
So for our drone, this might show how the autopilot processes sensor data to stabilize flight, but maybe not every tiny resistor and capacitor involved in that process.
You're right on target. And that brings us to the principal full scheme. This is the truly comprehensive blueprint, the nitty-gritty.
The main one.
Yeah, pretty much. It defines the complete composition of all elements, every single connection, and provides a detailed understanding of how the entire product operates. This is the foundational document, the one that directly informs the physical PCB design. If you're going to actually build a circuit, this is the one you absolutely need.
So those first three are really the electrical blueprints, moving from abstract function down to incredibly precise detail. But our sources also mention other types of schemes. Are they more about the physical reality of building it?
That's a great distinction. Yes. Beyond the core functional definitions, you have schemes that describe the physical reality and assembly process. The connection assembly scheme, for example,
Okay.
illustrates the actual physical connections between components. This includes harnesses, cables, maybe even things like pipelines in more complex industrial systems. Think of it as the wiring diagram for assembling the actual drone.
And a connection scheme, type 5. That sounds like it shows where you plug things in, like ports.
Correct. It shows the external connections of the product, like where you plug in a charger, a USB cable, or maybe an antenna.
Makes sense.
Then there's the general scheme, which defines the composite parts of a very complex system and their interrelationships, useful for large-scale systems integrating many subunits.
Yeah.
And the location scheme, which specifically determines the relative physical arrangement of component parts and their connecting wires or cables on the board or chassis.
So the location scheme is more about physical placement, whereas the principal scheme is all about the electrical connections. This layered approach makes so much sense.
It allows engineers to focus on different aspects of the design at different stages.
And there's even a combined scheme for when you mix and match.
Precisely. That happens when a designer needs to present different levels of detail or different aspects of the system, like function and location, within a single drawing. It helps keep all the relevant information consolidated in one place.
That makes sense. Now, designing these schematics isn't just a free-for-all drawing exercise. There are core principles and best practices that make them universally understandable to engineers around the world, right?
Indeed. One fundamental principle is symbolism and numbering. Components are represented by standard graphical designations. Think specific shapes for resistors, capacitors, transistors, etc.
Standard icons.
Exactly. And for clarity, especially across multiple sheets in a large schematic, components are sequentially numbered. For example, R1, R2, R3 for resistors, or S1, S2 for switches. This standardization ensures universal understanding among engineers, no matter where they are or what project they're working on.
So if I see R5 on page 1 and R5 on page 3, I know it's referring to the exact same specific resistor. It's like a universal component ID within that design.
Precisely. Connection representation is also crucial. Electrical connections are depicted using lines and junctions in a way that ensures a clear understanding of the circuit structure and operational principles, basically, how the current flows and signals travel.
It sounds incredibly precise, but also potentially very cluttered. What if you have a ton of identical components, like say 20 resistors all connected in parallel? Do you have to draw every single one?
Thankfully, no. Component grouping and simplification is a key practice to avoid that kind of visual clutter. In cases of multiple identical elements like parallel or sequential resistors, they can be represented in a simplified manner.
How?
Often, dashed lines are used to indicate these connections without drawing every individual component symbol. For instance, a bridge rectifier, which technically consists of 4 diodes, can be shown in a simplified single-block symbol form rather than drawing all 4 diodes individually. This maintains clarity without sacrificing accuracy.
That's smart. It keeps the diagram readable and focused on the function. What about the performance side? Do these blueprints tell you about things like voltage and current?
Absolutely. Schematics should also specify input-output characteristics. This often includes tables detailing contact numbers or pin numbers and their corresponding circuit characteristics like expected frequency, voltage levels, and current draw or sourcing capability.
Ah,
This provides vital information for anyone testing the circuit or integrating it into a larger system. It's not just what the circuit is, but what it does electrically at its boundaries.
and finally, the element list. What's that about? It sounds like a shopping list.
Pretty much. An element list must accompany every principal electrical scheme. This list unambiguously identifies all elements included in the design.
Every single part?
Every single one. It's typically found on the first sheet of the drawing and provides essential data. The item's position or reference designator, like L1 for an inductor, R1 for a resistor, C1 for a capacitor, S1 for a switch, its name or description, the quantity used in the design, and any relevant notes like tolerance or voltage rating.
Okay.
It's essentially the bill of materials, or BOM, tied directly to your blueprint. This ensures that every piece of the puzzle is accounted for and correctly identified throughout the product lifecycle. It's absolutely critical for procurement, assembly, and maintenance down the line.
So you've got your conceptual idea for the drone, your requirements are clear, and now your detailed schematic is complete. The next massive step is translating that electrical blueprint into a physical printed circuit board, or PCB.
Yep, making it real.
This is where specialized electronic design automation, or EDA, software really shines.
Exactly. These tools are the bridge between those abstract schematics and the tangible hardware. Industry standards like Mentor Graphics Expedition and Altium Designer are at the forefront of this process. They enable designers to meticulously plan the physical layout of the circuit, ensuring it's not just functional electrically, but also manufacturable and reliable physically.
I know these programs can look super intimidating when you first open them up. They're just packed with buttons and options everywhere, but there's a general workflow that's pretty consistent across them, which is helpful, right?
Yeah, definitely. You always start with project creation. You create a new project file, and then you either import or link the necessary schematic files and the component library files.
Linking them together.
Right. This connects your electrical design, the schematic, to the physical layout environment, ensuring everything you designed logically is now ready to be placed physically on the board.
And speaking of components, the libraries sound like a big deal. I imagine it's not just about what a component does electrically, but what it looks like physically on the board, its shape and size.
They are absolutely vital. Component libraries contain both parts of that equation, the schematic symbols, which you use for the electrical diagram,
The blueprint part.
and the physical footprints, which dictate exactly how the component sits on the PCB, lay out the pads, the outline, the dimensions.
Got it.
Modern tools often include helpful features like a symbol wizard and a footprint wizard to aid in creating these, especially for complex parts like big microchips or multi-pin connectors. These wizards allow users to define pin counts, types, and crucial physical dimensions, saving a tremendous amount of tedious manual work.
So the software knows not just what a resistor does, but its exact physical shape and pin locations. That seems like a huge time saver. And once you're in the software, how do you set up your workspace for, precision?
Working environment customization is key to efficiency and accuracy. Users can set the working units, whether that's millimeters or mils, which are thousandths of an inch.
Mils, right, common in electronics.
Very common, and you define grid spacing, which is crucial for precise placement of components and routing of traces. Snapping to a grid keeps things aligned.
And the display control, I've heard that can be a real learning curve, especially with multi-layered boards. So much going on.
It definitely is, but it's essential for managing complexity. Display control manages exactly what is visible and editable on your screen at any given time. You can toggle the visibility of various layers, like the different copper layers, the top and bottom silk screen layers, the solder mask layers.
The different films that make up the board.
Exactly. And you can toggle specific object types, such as components, traces, vias, which are the connections between layers, or the net lines, which show where connections should go before you route them.
Okay.
This helps manage visual complexity, especially during the intricate routing process where things can get very dense. For example, you might activate a function to display only the active routing layer you're currently working on.
So you can hide everything you're not working on right now, so it's not just a chaotic mess on screen. That makes perfect sense.
Precisely. It lets you focus.
And what about modes? I've heard these programs have different modes of operation. What's that about?
Yes, the concept of modes of operation is fundamental. These modes determine what actions you can perform and what objects you can select and edit.
Like different tools.
Kind of. For example, in component mode, you can move, rotate, and place components. In root mode, you're specifically drawing the copper traces and dropping vias. And in draw mode, you might be creating graphical objects like the board outline itself, or adding text, or defining keep-out areas.
So you have to be in the right mode for the task.
Exactly. If you try to route a trace while you're in component mode, it simply won't work, which can be frustrating if you're not aware of the mode you're currently in. It's like having different tools in a toolbox. You have to consciously pick the right one for the job.
So you have to be in the right mindset, and the software has to be in the right mode. And I imagine these tools rely heavily on efficiency, so there must be a lot of keyboard shortcuts.
They absolutely do. These tools heavily rely on keyboard shortcuts and function keys for efficiency. For instance, a single key press like F2 might pick up a component. F3 might start routing a trace, rather than navigating complex menus.
That speeds things up.
Massively. This speed and fluidity becomes second nature to experienced designers, allowing them to work much faster and more intuitively. The escape key is also incredibly important. It usually resets the current command or selection, preventing the software from getting confused, ensuring you always maintain control over what you're doing.
Good tip. Hit escape often. And what about feedback from the software? How do you know if you're doing things correctly or if there are potential problems?
The information displays are crucial for that. There's usually an XY coordinate readout showing your cursor's precise position on the board. And very importantly, there's a message window or status bar that displays errors, warnings, or helpful prompts, from the software.
Like a little assistant telling you what's going on.
Exactly. These are your real-time feedback mechanisms, constantly guiding you through the design process and alerting you to potential issues, like if you try to place a trace too close to another one.
Okay, so you've got your environment set up. Now, let's talk about actually creating the physical PCB layout. Where do you even begin with the board itself, the shape?
The very first step for the physical board is board outline definition. You have to define the shape and size of your PCB. This is typically done by drawing primitive shapes, lines, arcs, circles, other geometries on a specific layer, often called a keep-out layer or a dedicated mechanical layer.
So you draw the shape first.
You draw the boundary. Then, once drawn, this outline is converted by the software into the actual board shape. This process allows for incredibly complex board geometries, maybe not just rectangles, but weird shapes to fit into an enclosure, and also cutouts within the board itself, like mounting holes or slots for connectors.
Right. Drones often have custom shapes. So you draw the shape of your drone's brain first, then you put the components on it.
Exactly. Once the board outline is defined, component transfer occurs. The software takes all the components you defined in your schematic and brings them into the PCB layout environment. They often appear initially off to the side of the board outline.
Just a big pile of parts.
Sometimes, yeah. But often the software organizes them into logical groups or rooms that correspond to the functional blocks you might have defined in your schematic. This makes the initial placement more manageable, like moving furniture into predefined rooms in a new house instead of dumping it all in the driveway.
And when you start placing them, dragging them onto the board, are there any best practices for where things should go? Like, what's the first thing you consider?
Definitely. For initial component placement, several strategies are employed. A common requirement, especially for manufacturing efficiency, is to place all through-hole components, the ones with legs that go through the board on one side, typically the top layer,
Okay.
and then place all surface mount devices, or SMDs, the tiny ones that sit on pads on the other side, for instance, the bottom layer. The software often makes it easy to move components between layers, sometimes by just holding a key like Alt, or pressing L in Altium Designer while dragging the component.
I can imagine connectors would be important to place early, since they determine how the drone connects to everything else. Wires, antennas.
You're spot on. Connector placement is crucial and should be done early. Connectors should ideally be placed at the edges of the PCB. This facilitates enclosure design later on and ensures easy access for plugging in cables during assembly and in the final product.
Yeah,
You don't want connectors buried in the middle of the board.
makes sense. And checking for collisions, things bumping into each other.
That's where the 3D view becomes invaluable during placement. Most modern EDA tools offer a realistic 3D visualization of the board with components placed. This allows you to visually inspect the component arrangement and quickly identify any physical overlaps or clearance issues. These problems are often indicated by highlighting, maybe in green, within the software.
So you can spin it around and look at it from all angles.
Exactly. It's a fantastic way to catch physical fit errors before they become costly manufacturing problems. It's like having a virtual prototype right there on your screen.
Okay, we've designed our circuit, built its blueprint, and planned its physical layout on the computer. Now we're getting to the really exciting part, bringing this digital design into the physical world through manufacturing. And when we're talking about high-performance electronics like those in a drone, there's one term that constantly comes up: controlled impedance.
Yes, absolutely. One of the most critical aspects of modern high-speed electronics design is controlled impedance, often abbreviated as CI.
What is it, fundamentally?
It refers to the characteristic impedance of a transmission line. And on a PCB, that transmission line is formed by the copper traces and their associated reference planes, usually ground or power planes nearby. It's measured in ohms, and it becomes profoundly important when high-frequency signals are propagating on the PCB.
So why does it matter so much? Is it just about making things go faster, or is there something else?
It's primarily about signal integrity, ensuring the propagation of signals without distortion. At high frequencies, say typically above 100 megahertz or even lower for some sensitive signals, PCB traces no longer act like simple wires. They behave like transmission lines.
Okay, like tiny highways for signals.
Exactly. And think of it like this. If you shout into a canyon, you hear an echo. Right?
Yeah.
If that echo is too loud or arrives at the wrong time, it messes up your original message. On a PCB, if the impedance, which is essentially the resistance the signal sees as it travels, varies along the path, you get electrical reflections.
Ah, electrical echoes.
Precisely. These reflections superimpose on the primary signal, causing distortion, ringing, overshoot, things that can render the signal unusable. This is absolutely critical in applications like DDR memory for processors, HDMI for video signals, gigabit Ethernet for networking, and RF circuits for radio communication, all of which are essential in a modern drone.
Right, all high-speed stuff.
A uniform, controlled impedance minimizes these distortions, allowing the signal to arrive at its destination clean and clear without its own echo getting in the way and corrupting the data.
That makes so much sense. So the key insight here isn't just about the circuit design itself, but that the very material and structure of the board itself becomes an active part of how those high-speed signals behave. It's not just a passive canvas, it's part of the electrical painting.
That's a perfect way to describe it. The PCB stack-up is part of the circuit at high frequencies.
So what factors actually affect this controlled impedance? What do designers need to control?
It's a complex interplay of both the materials used and the physical dimensions of the traces and layers. The PCB materials themselves play a huge role.
What about them?
Key factors include things like the resin content percentage in the laminate, the dielectric constant decay values of that resin, and even the specific type of glass cloth weave used in the prepreg and core materials that make up the board layers.
Wow, even the weave of the fiberglass.
Yes. Different materials have vastly different decay values and also dissipation factor, DFA values, especially at high frequencies. These directly impact the impedance and also how much signal is lost as heat. Common materials like FR370HR, iSpeed, Megtron 6, Rogers 4350B, they all have different properties tailored for different needs. It's like choosing the right type of asphalt for a high-speed highway. The material itself affects the performance and durability.
So not all those greenish PCB materials are created equal when it comes to high-speed signals. I hadn't really thought about the board material itself being so actively important.
Absolutely not. They vary hugely. And beyond the materials, the physical PCB tolerances during manufacturing are critical. Even minute variations in the final etched trace height and width, both at the top and bottom of the trace, directly influence the resulting impedance. Manufacturing precision is absolutely paramount.
Like building that perfectly level road again.
Exactly. Even a tiny bump or variation in width can cause impedance discontinuities and problems at high speeds.
So how do engineers actually design for controlled impedance? Do they just guess the right trace width, or is it a more calculated process?
Oh, far from it. It's very calculated. The first step is to identify critical signals. The electrical engineers designing the circuit, or often the data sheets for the integrated circuits being used, must explicitly specify which signal nets require a particular controlled impedance.
So the chip manufacturer might say, these data lines need to be 100 ohms differential.
Precisely. As we mentioned, DDR memory traces, HDMI traces, gigabit Ethernet pairs, RF signal paths are prime examples. Data sheets often provide very detailed guidelines for the target impedance values, tolerances, and sometimes even recommendations for which layers to route them on.
And they put this right on the blueprints, right? So the schematic tells the PCB layout designer what needs special treatment later.
Yes. Schematic annotation is a crucial part of good design practice. The schematic should clearly mark the CI signals. For example, differentiating differential pairs with N and P polarity indicators and explicitly stating the target impedance values, like 180 IF for differential pairs or 50 ASE for single-ended nets.
Okay.
This communicates the requirements directly and unambiguously to the layout designer and eventually to the PCB manufacturer, leaving no room for guesswork.
So it's a team effort with the manufacturer, too. They can't just take the layout design and run with it. They need to collaborate on the specifics of the board build.
Precisely. It's a critical collaboration. For trace parameters and manufacturer collaboration, the designers provide the desired impedance values and maybe a desired layer count. The manufacturer then takes that, considers the materials they have and their process capabilities, and calculates the feasible board, stack up the arrangement and thickness of all the layers and the specific trace dimensions, width and spacing, needed on each layer to actually meet those impedance targets within tolerance.
So it's a back and forth sometimes?
Often, yes. It's a collaborative process, ensuring that the theoretical design can be practically and reliably achieved with the chosen materials and the manufacturer's specific fabrication processes.
And there are some core physical relationships that drive this, right? Like making a trace wider or taller affects the impedance differently.
Yes, it's fundamental transmission line physics. Generally speaking, impedance is inversely proportional to the trace width, and the copper thickness, wider or thicker, means lower impedance.
Okay.
Conversely, impedance is proportional to the height of the laminate dielectric material between the trace and its reference plane further away, means higher impedance. and it's inversely proportional to the square root of the laminate's dielectric constant, R. Higher decay means lower impedance.
Wow. Okay. Lots to balance.
Understanding these fundamental relationships allows designers and manufacturers to make effective adjustments and trade-offs to hit the impedance targets.
All right, let's get into the nitty-gritty of laying out these critical traces on the PCB. We've talked about the importance of getting the impedance right. What are some of the key routing strategies or tactics for these controlled impedance signals?
There are several vital strategies, often documented as design rules. One simple but helpful tactic is to differentiate CI traces. To aid manufacturing inspection and control, make CI trace widths slightly different from standard signal traces. For instance, use 5.1 mil width for a 50 Zeroman trace if your standard traces are 5.0 mil. It just makes them easier to spot.
Like putting a little flag on the important ones. Smart.
Yeah. Then absolutely crucial for differential pairs, signals that travel as a matched pair, like for USB or Ethernet.
Right, two traces running together.
You must ensure symmetry. Route these pairs parallel to each other with constant spacing between them. Think of them like synchronized swimmers. They need to stay perfectly in step. Minimize any areas where that spacing widens or narrows, especially near component pads.
So keep them tightly coupled and parallel. What about spacing them from other signals?
Good question. That relates to general signal integrity and crosstalk reduction. You need to maintain minimum spacing. A common rule of thumb is the 3W rule. Ensure the spacing between adjacent traces that aren't part of a differential pair is at least 3 times the trace width. Sometimes 2W acceptable, but more space is generally better to prevent one signal interfering with its neighbor.
Like giving cars enough room between lanes on the highway.
Exactly. And speaking of keeping things clear, you must avoid components or vias between differential pairs. Placing components or even drilling vias between the two traces of a differential pair creates significant impedance discontinuities. It's like putting a pothole right in the middle of your data highway.
Bad news for signal integrity.
Very bad. You should maintain a keep-out area between them, maybe 30 mils wide or even 50 mils for critical clock signals. If you absolutely need serial coupling capacitors on differential pairs, place them symmetrically on both traces to minimize the discontinuity. Any vias used for the pair must also be symmetrical.
Okay, keep that path clear. What about the length? Do they need to be the same length?
Yes, length-matching differential pairs is critical for many high-speed signals that must arrive at the receiver at precisely the same time within a specified mismatch tolerance.
How do you make them the same length if one has to take a longer path?
You add little wiggles, called serpentines or meanders, to the shorter trace to compensate for the length difference. You try to place these compensation wiggles as close as possible to the source of the mismatch, like near a bend or where VS cause a detour. Interestingly, if two bends are close together, say less than 15 millimeters apart, they might actually self-compensate for length.
Wow, clever. Okay, what else?
A huge one. Provide a continuous reference plane. All high-speed signals require an unbroken reference plane, usually a ground plane layer, directly beneath or above them for their return current path. At high frequencies, the return current wants to flow directly under the signal trace.
So no gaps or splits in the ground plane under the trace.
Exactly. You must avoid split planes. Do not route high-speed signals over splits in the reference plane, as this breaks the return path and forces it to take a long roundabout loop, creating noise and interference. If crossing a split is absolutely unavoidable, use stitching capacitors placed very close to the signal path to provide a high-frequency bridge for the return current between the two plane sections.
Stitching capacitors, okay.
Similarly, avoid voids. Stagger vias in dense areas to prevent creating large holes or voids in the reference planes, ensuring a continuous path. And if you use a power plane as a reference instead of ground, you need stitching capacitors near where the signal enters and exits that reference area to allow the return current to flow between the ground and power plane smoothly.
So the return path is just as important as the signal path.
Absolutely critical. And related to that, tactic number 7, add stitching vias close to signal vias. When a high-speed signal, either single-ended or differential, switches layers using vias.
Goes from top to bottom, for example.
Right, you need to add stitching vias, which are just vias connecting the reference planes on the starting and ending layers, usually ground, very close to the signal vias. This allows the return current to efficiently switch reference planes right along with the signal, maintaining that tight coupling. If the reference plane itself changes net, for example, from ground to a power plane, then stitching capacitors are needed near the vias.
Okay, that's a lot to consider for just routing traces, but clearly vital for high-speed performance. So we've gone from the digital drawing board through layout, considered impedance, and applied best practices. The culmination of this entire PCB design process is the generation of precise manufacturing files.
Yep.
These are the documents that the fabrication house, the factory, actually uses to produce the physical board.
This is where all that meticulous digital design work gets translated into a format that the manufacturing machines can understand and build from. The most common and essential of these are the Gerber files.
Gerber files, I've heard that term. What are they exactly? Are they like a specialized PDF just for circuit boards?
You can think of them that way, sort of. Technically, they are ASCII vector files that describe each individual layer of the PCB. So you'll export a separate Gerber file for the copper patterns on the top layer, another for the copper on the bottom layer, maybe several for internal copper layer.
Each layer gets its own file.
Exactly. And then separate Gerber files for the solder mask layers, which define where solder resist coating goes, the silk screen layers, which contain the component outlines and reference text like R1, C1, and various mechanical layers like that keep out layer defining the board edge, or maybe layers for paste masks used in assembly. Each file is a precise instruction set for a specific part of the fabrication process, like photo plotting the layer patterns.
And how do they know where to drill all the holes? It seems like there could be thousands of tiny holes for vias and component leads.
That's handled by a different set of files, usually NC drill files, which stands for numerically controlled drill.
Ah, for the drilling machine.
Precisely. These files contain the numerical control data for the automated drilling machine. They precisely specify the XY coordinates for every single hole on the board, the exact tool diameter or drill bit size to be used for each hole, and maybe other drilling parameters like whether the hole is plated through or not. This ensures accurate placement and sizing of all vias and component holes, which is vital for the board to function correctly and for components to fit perfectly during assembly.
Okay, Gerbers for layers, NC drill for holes, and then once the bare board is fabricated, you need to put all the actual components on it. Are there special files for that assembly process too?
Yes, absolutely. There are various assembly and documentation outputs generated from the EDA tool. Many CAD tools can generate comprehensive PDF packages. These typically include assembly drawings.
What's on those?
They clearly show the component placements and their outlines on the board, often with reference designators, making it easy for assembly technicians or pick-and-place machines to populate the board correctly. And very often, these packages will also include a detailed bill of materials, or BOM.
The shopping list again.
Exactly. The list of all the specific components, resistors, capacitors, ICs, connectors needed for the assembly, usually including manufacturer part numbers.
So it's not just the bare board files, but also exactly how to populate it with the right parts in the right places.
Exactly. And beyond those main ones, additional reports like net lists, which detail all the intended electrical connections between components, can also be generated for verification purposes or for automated testing fixtures during production planning. These outputs collectively form the final instruction package, the bridge between the design environment and the physical reality of the manufactured and assembled circuit board.
All right, we've talked about the brain and the blueprint of our drone. Now let's bring it to life. How do you actually power one of these things, especially our sports aerial filming UAV, which needs to be nimble and relatively lightweight? Power is key.
The choice of power source for UAVs is absolutely critical, and it really depends heavily on the specific application and its requirements. For most multi-rotor drones that we see commonly,
Like quadcopters.
exactly, electric batteries, specifically lithium polymer or LiPo batteries, are overwhelmingly the preferred choice.
Why LiPo? What makes them so good for drones compared to, say, other battery types or even fuel?
Well, they offer several key advantages for this kind of application. LiPo batteries allow for very precise thrust control and, crucially, much faster response to throttle input. This rapid response is essential for the differential thrust needed in multirotors to make quick attitude adjustments and agile maneuvers vital for something like tracking a fast-moving athlete.
Faster reaction time than other sources.
Generally, yes, compared to combustion engines. Electric systems are also typically more reliable in terms of fewer moving parts compared to complex fuel engines and transmissions, minimizing the risk of a crash due to a sudden motor shutdown or mechanical failure.
I can imagine the main drawback is flight time, though. You can't just keep going for hours and hours like a gasoline engine could.
That's the primary trade-off, absolutely. Fuel systems using gas, gasoline, maybe even hydrogen fuel cells do offer much higher energy density and power, which translates to significantly longer flight endurance.
Right.
However, their transmission mechanisms are more complex, they're significantly heavier, and they generate more vibration and noise. They're typically reserved for larger UAVs where long endurance is the top priority.
So for our aerial filming application, where the video might just be a secondary source or short clips are needed, the shorter flight time of LiPo is okay.
Exactly. For this kind of use case, shorter flight times of, say, 7 to 15 minutes are often deemed acceptable, especially since LiPo batteries can be easily and quickly swapped out in the field between flights. It's a practical balance of power, weight, responsiveness, and operational needs.
So what kind of LiPo specs are you looking for specifically in a drone battery? Is it just about how big it is, the capacity?
Not just capacity, though that's important. Key selection features include high capacity, yes, but also high energy density, which translates directly to lower weight, absolutely crucial for flight efficiency.
More energy packed into less weight.
Precisely. A high discharge rate, often called the seed rating, is also vital. This determines how quickly the battery can deliver power, which is needed to meet the sudden, high current demands of vertical takeoff and landing, VTOL, and rapid acceleration during flight.
Got to handle those power spikes.
Exactly. And regarding the number of cells connected in series, usually denoted as S, like 3S or 4S, 3 or 4 cells are commonly recommended for small to medium drones. This voltage range is generally compatible with most common drone electronic components like motors and ESCs.
That makes sense, but simply having a battery isn't enough, especially with these powerful but somewhat sensitive lipochemistries. This brings us to the battery management system, or BMS, which sounds like it acts as the battery's own dedicated brain.
That's a great way to put it. A BMS is a specialized electronic system, a circuit board itself designed specifically to manage and protect lithium-based battery packs, Li-ion or LiPo.
Why is it so important for lithium batteries?
Given the sensitivity of these chemistries to things like overcharging, overdischarging, and temperature extremes, the BMS acts as the brain of the battery pack. It ensures safety, optimizes efficiency, and maximizes the longevity or lifespan of the battery. This is particularly crucial in high-performance, high-reliability applications like drones where a battery failure could mean a catastrophic crash and loss of the vehicle.
So what does this brain actually do? What are its key components inside? How does it work?
A typical BMS integrates several key components working together. First, you have sensors. These constantly measure vital parameters like voltage, current flowing in or out, and temperature, often for each individual cell within the battery pack, not just the overall pack voltage.
Monitoring every single cell. Wow.
Yes, that's critical for balancing. This data then feeds into a microcontroller, the actual processing unit of the BMS. It analyzes the data from the sensors against preset safety limits and algorithms.
And makes decisions based on that data.
Exactly. It triggers protective actions if needed, for example, commanding switching components, usually MOSFETs or sometimes relays, to disconnect the battery from the load during an overdischarge event to prevent permanent cell damage, or cutting off charge current if a cell voltage gets too high.
Okay, protection is key. What about keeping the cells healthy?
That's where balancing circuits come in. They are essential for redistributing energy uniformly between all the cells in the pack. Over time, cells can become slightly unbalanced to their charge levels. Balancing prevents this, ensuring no single cell gets overstressed, which prevents capacity degradation and extends the overall life of the battery pack.
How does it balance them?
It can be done passively, using resistors to bleed off excess energy as heat from the higher charged cells until they match the lower ones. Or it can be done actively, using more complex circuitry to efficiently transfer energy from higher charged cells to lower charged ones. Active balancing is more efficient, but also more complex and costly.
Got it. And does it talk to the rest of the drone?
Yes, typically there's a communication module. This relays critical battery status data like voltage, current, temperature, remaining capacity to the drone's main flight controller, usually via standard communication protocols like I2C, SMBus, or increasingly CAN bus, or even Bluetooth for wireless monitoring.
That's a lot of oversight packed into the battery itself. So just to summarize, what are the main functions of a drone BMS? It sounds like it's doing a lot more than just being a fuel gauge.
It absolutely does. The core functions encompass critical safety and performance roles. First, voltage and current monitoring prevents dangerous overcharging or overdischarging conditions for the pack, and importantly for individual cells, which can lead to thermal runaway or permanent damage.
Safety first.
Definitely. Second, cell balancing, as we discussed, maintains a uniform charge across all cells, which is vital for pack health, available capacity, and preventing premature degradation. Third, Thermal management monitors battery temperature, preventing overheating, which can cause fires, or operating at freezing temperatures, which drastically reduces performance and can also damage the cells.
And it does tell you how much juice is left, right?
Yes, that's city charge SOC estimation. It provides an accurate prediction of the remaining battery capacity or flight time, which is crucial for safe flight planning and avoiding unexpected power loss mid-mission. This is often more sophisticated than just measuring voltage. It uses algorithms that track energy flow.
More than just a simple voltmeter.
Much more. Additionally, built-in protection circuits safeguard against critical fault conditions like external short circuits and overcurrent events, acting like smart fuses. And fault detection capabilities can identify potential internal issues within the battery pack itself, such as loose connections between cells or internal shorts, providing early warnings. It's truly a comprehensive guardian for the battery system.
It sounds like an absolute necessity for safety and reliability, but I've heard that not all drones actually use batteries with an integrated BMS. What's the difference between, say, a traditional BMS and a smart BMS, and why isn't every drone flying with one today?
That's a great question, and there are nuances. A traditional BMS might offer just the basic protections over/under voltage, over current, maybe with passive balancing, fairly basic monitoring outputs, limited communication interfaces, and often fixed, non-configurable parameters.
Okay, the basics.
In contrast, a smart BMS represents a significant evolution. It often features more efficient active balancing, uses more sophisticated predictive algorithms, sometimes incorporating AI or machine learning capabilities for better SOC estimation and health prediction. State of health, SOH.
Smarter predictions.
Exactly. They usually have more advanced communication interfaces like CAN bus or UART or Bluetooth, allowing for more detailed data logging and control. They might have self-learning capabilities to adjust parameters based on usage patterns and offer customizable settings via software. A smart BMS truly excels in real-time optimization, detailed diagnostics, and even predictive maintenance warnings, making it more intelligent and adaptable.
So smart BMS offers a lot more intelligence and flexibility, almost like a dedicated computer managing the battery with predictive capabilities. But why don't many drones, especially maybe hobbyist ones, use batteries with any BMS today? Is it purely a cost thing or weight?
It's a combination of factors. Primarily, a BMS, especially more complex smart BMS, adds weight and volume to the battery pack. And in drones, every gram counts against flight time and agility. So there's a direct trade-off.
Right. Is always the enemy.
Always. Secondly, for many hobbyist and consumer-grade drones, and even some commercial racing drones where performance is paramount, pilots often use raw LiPo packs without an integrated BMS. They rely on external chargers that have built-in balancing features, performing the balancing function manually before or after flights. They essentially offload the BMS function to a ground-based device to save weight on the drone itself.
Ah, okay. Manage it externally.
Right. Also, some drone applications simply prioritize raw power density and minimum weight over the advanced safety, monitoring, and longevity features offered by a BMS, especially where flight times are short and batteries are treated almost as consumables, or where the operational risks are managed through other means.
So it's a conscious trade-off where sometimes the added complexity, cost, and weight of an integrated BMS aren't deemed worth it for certain types of applications or user preferences. But I imagine this is changing as drones become more integral to critical operations and safety regulations tighten.
Absolutely. As drone technology continues to advance, and the demand for longer flight times, enhanced safety, higher reliability, and more complex autonomous missions grows, the adoption of integrated BMS, particularly smart BMS, is definitely expected to increase significantly, especially in professional and industrial applications.
So which types of drones do really benefit from or even require a BMS? Where is it truly becoming non-negotiable?
Certain types of drones significantly benefit from or increasingly require BMS-equipped batteries. Industrial and enterprise drones, for instance those used for critical infrastructure inspection, precision agriculture, or public safety operations like search and rescue, absolutely need robust battery management for mission success, reliability, and safety compliance.
High-stakes applications.
Definitely. Long-endurance drones, those designed for extended flight times for missions like surveillance, mapping, or package delivery, rely heavily on optimized battery management provided by a BMS to maximize their operational range and ensure they can complete their mission safely.
Makes sense for long flights.
Heavy-lift drones, such as those designed for carrying significant cargo payloads, need stable voltage delivery under heavy, fluctuating loads, which a well-designed BMS helps provide by managing cell performance. And finally, Systems using high-voltage battery packs, maybe 12S or even higher configurations, are inherently more susceptible to cell imbalances, making a BMS practically essential for safe and efficient operation.
Got it. And for those engineers looking to integrate a BMS into their drone battery design, are there best practices? What makes for an optimal BMS setup to ensure it works reliably?
Yes, for optimal performance and reliability, several best practices are recommended. Cell matching is crucial. Ideally, use battery cells from the same manufacturing batch with closely matched characteristics to minimize inherent imbalances right from the start.
Start with good cells.
It's exactly. Thermal design is critical. Embed temperature sensors strategically near potential hotspots within the pack and ensure the BMS can effectively monitor and react to temperature changes. Consider heat sinking or airflow if needed. Regularly perform firmware updates for the BMS microcontroller, as manufacturers often release updates with improved algorithms, new features, or bug fixes.
Your brain updated.
Yep. Rigorous testing under real-world operational conditions, including vibration, shock, and temperature cycling, is absolutely essential to validate the BMS performance and reliability before deployment. Designing for modularity can be beneficial, allowing for easier replacement of faulty cells or BMS components without replacing the entire expensive pack. And always consider using lightweight BMS components where possible to minimize the weight penalty, and potentially incorporate redundancy in monitoring or protection circuits for critical missions where a single point of failure in the battery system could be catastrophic.
Okay, so we've got the power source intelligently managed, hopefully with a good BMS. Now, let's talk about how the drone actually moves and flies, translating those electrical impulses from the flight controller into physical motion. This involves electronic speed controllers, or ESCs, and the true brain of the operation, the autopilot.
Right. The ESCs are essentially the motor managers. Their primary function is to take the command signal from the flight controller, typically a pulse width modulation, or PWM signal, or a digital signal like D-Shot, and convert that into the precisely timed electrical power sequence needed to make a brushless motor spin at the desired speed and direction.
So they're the translators between the flight controller's brain and the motor's muscle, telling the motors exactly how fast to spin.
Exactly. They handle the high power switching needed to drive the motors. ESCs contain built-in firmware, which is like their own mini operating system that controls their behavior and features, like setting a cutoff voltage to protect the battery or enabling braking functions to stop the propeller faster.
Firmware again. Seems important everywhere.
It is. It's crucial to ensure the ESC is electrically compatible with the motor it's driving, in terms of voltage and current rating, and that the control signals are properly calibrated between the flight controller and the ESC. Many ESCs also include a small voltage regulator called a battery eliminator circuit, or BEC.
BEC, what's that for?
It eliminates the need for a separate small battery to power the flight controller or radio receiver. The BEC taps power from the main flight battery and steps it down to a lower voltage, typically 5V, to power these low-power electronics, simplifying the overall power system wiring.
Ah, convenient. And that firmware you mentioned inside the ESCs, that sounds incredibly important. It's the software that really breathes life into these motors, determining how they respond to commands.
It absolutely is. The ESC firmware is the core software running on the ESC's own microcontroller. It determines all its configurable settings with communication protocols it understands like PWM, D-Shot, etc., and the user interface for configuring it. And importantly, each firmware version is designed for specific ESC hardware-specific processors and power stages. So you can't just load any firmware onto any ESC. That has to be compatible.
So for FPV drones especially, where responsiveness is key, how has this ESC firmware evolved over time? I imagine it started relatively simple and got much more complex and faster.
It's been a fascinating and rapid evolution, driven largely by the FPV community demanding better performance. In the early days, around 2011, Simon K firmware was a popular open-source option that greatly improved responsiveness over stock firmware. Then came BL Heli in 2013, another open-source project.
BL Heli, I hear that name a lot.
Yeah, by around 2015, BL Heli became the sort of unofficial standard. It offered broad hardware compatibility, a lot more features, it was user-friendly to configure, and had continuous updates from the community. A game-changing feature it introduced early on was active braking, also called damped light.
Active braking.
It actively uses the motor's back EMF to slow down the propeller much faster when the throttle is reduced, rather than just letting it freewheel. This dramatically enhanced responsiveness and flight stability, making drones feel much more locked in.
So BL took over as the dominant player back then. What came next after that? How did it improve further?
In 2016, BL Hellas emerged. This was an upgrade specifically designed for ESCs using faster BiSi-B, BB1 and BB2 processors. Hardware was getting better. BL Hellas itself brought incremental improvements, but its main significance was enabling the hardware to support the revolutionary digital D-SHOT protocol, which we'll discuss more in a moment. It marked the shift away from analog PWM signals.
Okay, faster processors enabling digital signals. Then what?
Then, in 2017, came BL Healy 32. This was a major leap, designed specifically to leverage the new generation of powerful 32-bit processors appearing on ESCs, moving beyond the older 8-bit ones. This extra processing power enabled much more advanced features.
Like what kind of features?
Things like ESC telemetry, the ability for the ESC to send data back to the flight controller, like real-time motor RPM, temperature, voltage, current draw. Also, customizable startup tones, higher PWM frequencies for potentially smoother motor control, and more sophisticated motor control algorithms. BL Healy 32 is closed source, however, requiring licensed hardware.
So a clear progression towards more processing power, more intelligence, and more feedback from the ESC. Are there even newer options that have come out since BL Healy 32?
Yes, the innovation continues. AM32, which emerged around 2020, is an open-source firmware alternative aiming to provide BL Healy 32-like features on supported 32-bit ESC hardware. Some new ESCs are shipping with AM32 pre-installed, and more recently, in 2022, BlueJay firmware appeared. This is interesting because it's designed for the older, cheaper BL Healy's 8-bit hardware, but it cleverly unlocks features previously exclusive to 32-bit ESCs, like bidirectional D-SHOT, which needs telemetry, and custom startup tones, bringing advanced capabilities to more affordable hardware through software ingenuity.
Wow, keeping older hardware relevant. That's cool. So when you buy an ESC, how do you know what firmware it has?
Typically, ESCs come with firmware pre-installed by the manufacturer, usually BL Helix or BL Healy 32 or BAM32 now, and this is almost always indicated clearly in the product description or specifications.
That brings us neatly to ESC protocols, the actual languages of communication spoken between the flight controller and the ESC. How do these different languages work? It's not just a simple on-off switch, is it telling the motor to spin?
Not at all. ESC protocols are the specific way the flight controller commands the ESC to spin the motors at a desired speed. We can broadly categorize them into the older analog protocols and the newer digital protocols, with each generation representing a leap in precision, speed, and noise immunity.
What were the early analog ones, and what made them less ideal for high-performance drones as things evolved?
Earlier generations used analog protocols. Standard PWM, the original method from way back, used pulses varying between 1,000 and 2,000 microseconds. It was simple, but relatively slow and susceptible to timing jitter.
The old RC standard.
Pretty much.
Yeah.
Then came faster analog options like One-Shot 125, using 125 250 microsecond pulses, and One-Shot 42, even faster at 4284 microseconds. These offered shorter signal widths, leading to lower latency, and were designed to better synchronize with the flight controller's main processing loop, the PID loop, reducing jitter and delay compared to standard PWM. Multi-Shot, with its tiny 525 microsecond signal width, was the fastest of the analog protocols.
But still analog. What was the limitation?
The fundamental limitation with all analog protocols is their susceptibility to electrical noise and interference. The signal level is represented by the pulse width, and noise can distort that width, leading to imprecise motor control, especially in the electrically noisy environment of a powerful drone.
And the big leap, D-Shot, is digital, right? What was the game changer there? Why is digital better?
Yes, D-Shot represented a significant leap forward precisely because it's a digital signal, contrasting sharply with the analog nature of all its predecessors. Being digital means the command is sent as a binary number, a sequence of ones and zeros.
So it's either a 1 or a 0, much harder to corrupt by noise.
Exactly. It offers vastly improved reliability and performance because it's inherently much less prone to noise and interference. It also includes error checking and checksum, so corrupted commands can be detected and ignored by the ESC. Plus, D-Shot allows the transmission of specific commands to ESCs embedded within the speed signal itself, not just motor speeds, which opens up new control possibilities like reversing motor direction via software.
Very cool. And you mentioned ESC telemetry with BL Healy 32. How does D-Shot enable that?
That comes with bidirectional D-Shot. This is a clever extension where the ESC can actually send data back to the flight controller over the same signal wire normally used just for commands. It interleaves telemetry packets like motor RPM with the command packets.
Two-way communication on one wire.
Yeah. This feedback enables really powerful features in the flight controller firmware, like RPM filtering. By knowing the exact RPM of each motor, the flight controller can precisely filter out the noise generated by the motors and propellers from the gyroscope sensor data, leading to much smoother flight and potentially allowing for higher PID gains, more responsiveness. It also enables features like dynamic idle, where the flight controller can adjust the motor's idle speed based on RPM feedback for better stability and efficiency.
So it's not just sending commands blindly anymore, it's a closed-loop system with feedback, making the whole flight control system much smarter. That sounds incredibly useful. Now, are there different D-Shot speeds, like D-Shot 150, D-Shot 600, D-Shot 1200, and is faster always better? Should everyone just run the fastest possible?
That's a common question. Yes, there are several D-Shot speeds, indicated by the number, which roughly corresponds to the data rate in kilobits per second. For example, D-Shot 600 is about 600 kilobps.
Higher D-Shot numbers mean a shorter time to transmit each command packet, offering theoretically reduced latency. D-Shot 150 takes about 106 microseconds per command, while D-Shot 2400 takes only about 6.7 microseconds.
Huge difference, so faster is better, right?
Not necessarily. While lower latency is good in theory, these higher speeds also carry an increased risk of data corruption due to noise, especially over longer wires or in noisy environments. They also place a higher processing load on both the flight controller's CPU and the ESC's processor.
The trade-off again? It's exactly. Betaflight, which is a very popular open-source flight control firmware, often recommends matching the D-Shot speed somewhat conservatively to the flight controller's main PID loop frequency. For example, D-Shot 300 might be fine for a 4 kHz PID loop, and D-Shot 600 for an 8 kHz loop. Pushing to D-Shot 1200 or D-Shot 2400 might not yield noticeable flight performance benefits for most pilots because the latency differences are already down in the microseconds range, but it does increase the risk of glitches caused by corrupted packets, which could lead to erratic motor behavior.
So find the reliable sweet spot, don't just crank it to max.
Pretty much. It's about finding the right balance between speed, reliability, and CPU load for your specific hardware setup. Faster isn't always better if it introduces errors or strains the system. Much like choosing the right gear for a car, flooring it in first gear isn't always the fastest or most efficient way to drive.
Okay, so that handles telling the motors precisely what to do. Now, for the true brain of the UAV, the thing making the decisions, the autopilot, like the commonly used Pixhawk platform. This is where all the sensor data comes together to make sense of the drone's position, orientation, and movement.
The autopilot is absolutely the central control unit, truly the brain of the UAV system. It's responsible for the drone's stabilization, just keeping it level, and its navigation, whether it's being flown manually by a pilot or executing an autonomous mission in automatic flight modes.
How does it do that?
It constantly processes a flood of data from various sensors like accelerometers, gyroscopes, GPS, barometer, and based on that data and the desired flight path or pilot commands, it calculates and sends the appropriate commands to the actuators, mainly the ESCs controlling the motors, to adjust the drone's flight attitude and position. It's essentially performing thousands, maybe tens of thousands of calculations per second just to keep the drone stable and on course.
That's intense. And Pixhawk is an open source project, which is a big deal in the drone world, right? What's the advantage of that in a complex system like this? Why not just use proprietary systems?
It's a huge advantage for several reasons. Open source projects, OSPs, like Pixhawk, and the associated flight control software that runs on it like ArduPilot or PX4 significantly reduce development costs because the hardware designs and software code are freely available. This fosters immense collaboration among developers, researchers, and companies worldwide, allowing for the rapid exchange of both hardware improvements and software features.
So a whole community builds and improves it.
Exactly. And crucially, for advanced applications, it enables users to modify the core UAV software. This is vital for integrating custom functionalities, like specialized sensor drivers or complex algorithms for things like computer vision-based navigation or, in our example, automatic object tracking for aerial filming. You have the freedom to adapt the platform to your specific needs, which is often impossible with closed proprietary systems.
So it's not just a fixed, ready-made product, but a powerful, flexible platform you can build on and customize. What kinds of advanced features can a system like Pixhawk handle comparable to maybe more expensive commercial systems?
Pixhawk hardware, running mature open-source firmware, offers advanced features very similar to many proprietary systems. This includes robust GPS-based waypoint navigation, sophisticated automatic takeoff and landing routines, intelligent battery fail-safe behaviors, support for gimbal control for camera stabilization, and compatibility with a wide variety of automatic flight modes and different ground control station GCS software options.
That sounds pretty capable.
It is. And a unique and highly relevant feature for our deep dive today is that platforms like Pixhawk have increasingly incorporated partial integration or interfaces for vision systems. This lays the groundwork for more advanced vision-based navigation and control, meaning the autopilot can start to see and react to its environment using cameras, not just rely on GPS and inertial sensors.
Getting closer to true autonomy. And the autopilot hardware itself isn't just one single chip, right? It's typically a board with a collection of integrated modules all working in concert. It's like a complex system within the larger drone system.
Precisely. It's a highly integrated board. Within a typical modern autopilot like a Pixhawk, you'll find several key integrated modules. There's the core sensor module, which usually includes an inertial measurement unit, or IMU.
The IMU, right, measures movement.
Yes, the IMU contains accelerometers to measure linear acceleration, rate of movement change, and gyroscopes to measure angular velocity, rate of rotation for yaw, pitch, and roll. This raw data is fed into complex estimation algorithms like an extended Kalman filter, EKF, which fuse it with other sensor data to produce an accurate estimate of the UAV's attitude, orientation, and position. Often there are multiple redundant IMUs for reliability.
What else is in there?
Usually magnetometers, basically digital compasses, to help estimate heading or yaw, especially when GPS is weak. A barometer provides barometric altitude estimation by measuring air pressure. There's interfaces for an external GPS module, which is crucial for providing absolute position, geolocalization, and enhancing the accuracy of the estimators, enabling automatic flight modes like waypoint navigation.
Safety features.
Yes, a dedicated safety module or safety coprocessor might be included, continuously monitoring the health of the main processor, sensors, and software to prevent, detect, and manage failures, triggering fail-safe actions like returning to launch if something goes wrong, ensuring safe operation.
And the main processor.
That's the control module, the main processing unit, often a powerful ARM Cortex microcontroller that runs the flight control firmware, executes the complex control algorithms, and generates the command signals for the actuators based on the fused sensor inputs and mission plan. And finally, the communication module handles all the interfaces and protocols for connecting to external devices, the radio receiver, telemetry radio, GPS, ESCs, companion computers, sensors via UART, I2C, SPI, CANID, etc. It's the hub connecting the brain to everything else.
That's a lot packed onto one relatively small board. And outside the drone itself, you need a way to monitor and control it, especially for complex missions, right? That's where ground control stations, or GCS, come in. It's like mission control for your drone.
Exactly. GCS are typically land-based control centers, often software running on a laptop, tablet, or dedicated controller that provide human operators with the facilities to plan, monitor, and control UAV operations.
What can you do with a GCS?
They allow real-time monitoring of the drone's status position, altitude, speed, battery level, sensor readings, system health, fail-safe states. You can use them to configure autopilot parameters, upload mission plans with waypoints, switch between different flight modes, manual, stabilized, autonomous, and often manually intervene if needed. They also typically log detailed flight data for post-mission analysis and diagnostics.
So they're pretty critical for complex flights.
Absolutely critical, especially for managing autonomous flight modes, ensuring situational awareness, and preventing crashes by providing that essential human oversight and intervention capability.
And Mission Planner is a good example of that kind of software.
Yes. Mission Planner is a very popular, full-featured, open-source GCS application primarily used with the ArduPilot firmware. It serves as both a powerful configuration utility for setting up the drone and a dynamic control supplement during flight, with telemetry hardware linking the GCS computer to the drone.
That radio link we talked about.
Right. Mission Planner allows real-time UAV status monitoring on a map interface, recording detailed telemetry logs, which are often much more comprehensive than the logs stored on board the drone itself, and tools for analyzing those logs after the flight. It also often integrates features for first-person view, FPV video display, if the drone is equipped with an FPV camera and transmitter.
So with all these intricate systems and modules, autopilot, sensors, ESCs, GCS, how do they all talk to each other reliably? This brings us to the specific communication links and protocols speaking the digital language. It's definitely not just a simple wire connecting everything, is it?
Not at all, especially inside the drone and between the drone and the ground. This is where the world of sensor interfaces and communication protocols becomes crucial. Within the embedded system, we generally rely on four dominant communication standards or protocols for transferring data between the main computing resources, like the autopilot or an onboard companion computer, and various sensors or peripherals. Each has unique characteristics, strengths, and weaknesses.
Making one often more appropriate than others depending on the specific need, right? Speed, distance, number of devices.
Exactly. It's about choosing the right tool for the job.
Let's quickly recap those four main internal ones. Start with UART. What's its specialty again? Simple stuff.
UART, or Universal Asynchronous Receiver Transmitter, is generally the simplest. It's a two-wire bus with one wire for transmit, TX, and one for receive, RX, enabling full duplex communication. It's asynchronous, meaning there's no shared clock signal. Both devices must be pre-configured to operate at the same speed, the baud rate.
Baud rate, right, like 9600 or a 11500 and 200.
Exactly. It's primarily designed for one-device-to-one device communication. Range depends a lot on the implementation and speed, but it's typically for connections within a device or over short cables. Speeds commonly range from 9600 up to maybe 1 megabit per second or sometimes higher. Data is transmitted in packets framed by start and stop bits.
So what's it good for on a drone?
Ideal for simple, direct point-to-point connections. For example, connecting the GPS module to the autopilot or connecting the telemetry radio module. It's straightforward, but doesn't easily support multiple devices on the same two wires. Think of it as a dedicated, simple phone line between two specific people.
Okay, simple and direct. What about I2C? I hear that one's good when you have lots of sensors to talk to.
It is indeed.
Yeah.
I2C, or Inter-Integrated Circuit, is also a two-wire bus, using SDA for data, serial data, and SCL for clock, serial clock. Crucially, it's synchronous. The master device generates the clock signal on the SCL line, keeping all communications synchronized.
Master and slaves.
Right. It operates with a single master, multiple slave architecture. Each slave device on the bus has a unique 7-bit address, though 10-bit addressing exists, allowing the master to talk to up to 128 different devices theoretically, though 16 addresses are reserved. Standard speed is 100 kilobits, with faster modes up to 1 mbit or more. It's typically for short distances, maybe around 1 meter or less, often just on the same PCB. And it requires pull-up resistors on both the SDA and SCL lines.
So why use I2C?
It's excellent for interfacing many relatively low-speed slave devices like temperature sensors, humidity sensors, pressure sensors, barometers, magnetometers, maybe some IMUs with a single master controller, the autopilot. It minimizes wiring complexity and the number of pins needed on the master, making it very popular for integrating lots of environmental sensors without needing tons of wires. Think of I2C as a busy office intercom, where one manager, the master, can specifically call up and talk to many different employees, slaves, over just two shared wires. Standardized connectors like Stemma QT and QUIC make it even easier, almost plug and play.
SPI sounds like it's built for speed, though. Is it the fastest of these Talman ones?
Generally, yes, it's built for higher speed communication. SPI, or Serial Peripheral Interface, typically uses a 4-wire bus, though variations exist. SEK for the clock, MOVAT for master out slave in data, MISO for master and slave out data, and CS, or chip select, sometimes called slave select SS, which is a dedicated line from the master to each slave device.
Dedicated line per slave. That sounds like more wires.
It is. That's the trade-off for speed and simplicity in the protocol itself. SPI is synchronous, with the master generating the clock on SEK. It's typically a single master multi-slave setup. It offers very high speeds, often 10-20 MPs, sometimes much higher, and it supports full duplex operation. The master can send data on OMAN-I while simultaneously receiving data on MISO.
Wow, simultaneous talking.
Yeah. The range, however, is often limited, typically 10 centimeters or less, usually just connecting components on a single PCB. It also has no built-in error checking in the basic protocol.
So where would you use SPI on a drone?
SPI is often considered a de facto standard when speed and low latency are paramount. It's commonly used for things like interfacing with flash memory chips for data logging, controlling graphical displays if the drone has one, or talking to high-speed sensors like some faster IMUs, especially when only a limited number of such high-speed devices are needed. The wiring is more complex due to those dedicated chip select lines, but the speed advantage often makes it the right choice for data-intensive peripherals.
And finally, CAN bus. I usually associate that with cars. The OBD2 port uses it, right? What makes it good for robust applications like drones or industrial systems?
Yes, CAN, or Controller Area Network, is heavily used in automotive, But its robustness makes it increasingly popular in drones and robotics too. It's typically a two-wire bus using CAN-H high and CNL low lines. It employs a differential voltage signaling scheme, which makes it incredibly resilient to electrical noise, a huge advantage in vehicles or drones with powerful motors.
Differential signaling helps reject noise.
Exactly. A key feature of CAN is that there's no central master controller required for bus access. Instead, nodes use an arbitration scheme based on message IDs. Messages with lower ID numbers have higher priority and win access to the bus if multiple nodes try to transmit simultaneously. This makes it very deterministic and reliable.
Smart bus access.
It's well documented and standardized. ISO Allen 1898, offering good range, maybe 40 meters at the full 1 LBP speed, or up to 1,000 meters, 1 kilometer, if you reduce the speed significantly. However, it requires additional hardware, a dedicated CAN controller, often built into microcontrollers now, and a CAN transceiver chip to generate and receive the differential voltage signals. Your basic microcontroller pins can't connect directly to a CAN bus.
Extra hardware needed, so why use it despite that?
Because it was originally designed for the incredibly challenging electrical environment of cars, its reliability, noise immunity, and flexible multi-master capability make it ideal for robust systems like industrial automation or complex drones. It has a relatively high overhead per message for IDs, checksums, etc. But this ensures extreme reliability and fault tolerance, making it perfect for safety-critical systems or linking major subsystems together, like connecting the autopilot to smart batteries or smart ESCs that support CAN.
So those are the general communication standards working inside the drone. But our drone also has its own specific external communication needs and middleware to tie everything together, especially for autonomous flight and interaction with the pilot.
Yes, absolutely. Starting with the fundamental positioning system. Global Positioning System, GPS. This relies on receiving signals from multiple satellites orbiting Earth to calculate the drone's geographic location.
Essential for knowing where it is.
Crucial for autonomous flight modes like waypoint navigation or return to launch, allowing the autopilot to correct its estimated position. Accuracy depends on the number of satellites visible and signal quality, typically requiring an open view of the sky. Good GPS receivers with enough satellites locked might achieve around 1 meter accuracy.
And then the basic remote control stick inputs from the pilot. How does that link work?
That's radio control, RC. It establishes the primary link for direct manual piloting of the UAV. This involves a radio transmitter, the controller held by the pilot, sending signals to a radio receiver mounted on the drone. The receiver then typically outputs these control signals for throttle, roll, pitch, yaw to the autopilot, often as PWM signals or sometimes using faster serial protocols like SBUS or DSMX. These RC systems commonly operate in the 2.4 GHz band using techniques like digital spectrum modulation, DSM, or frequency hopping spread spectrum, FHSS, to improve signal robustness and resist interference.
Okay, that's for manual control. What about getting real-time data back from the drone to the pilot or GCS, like its battery level, speed, altitude, GPS status?
That's telemetry. This provides a downlink for real-time feedback on the UAV's system state, connecting the ground control station software with the autopilot via a pair of radio transceiver components, one on the drone, one connected to the GCS computer, often via USB.
Different frequency than the RC control.
Usually, yes. Telemetry systems typically operate on different frequencies like 433 MHz, 868 MHz, or 915 MHz, depending on regional regulations, specifically to avoid interfering with the 2.4 GHz RC control link. They use specialized communication protocols designed for efficiency and reliability over potentially long distances, like the MAV-Link protocol. Telemetry radios can have ranges from hundreds of meters up to several kilometers, enabling monitoring and even control via the GCS over much greater distances than the standard RC link might allow.
And you mentioned MAV-Link there. What is that exactly? It sounds like maybe the overarching language for drone communication between different parts in the ground.
MAV-Link communication protocol is exactly that in many ways. It's a widely adopted, open-source, lightweight messaging protocol specifically designed for communication between drones, ground stations, and onboard components.
Lightweight. Why is that important?
It's highly efficient with very low overhead, only 8 bytes per message packet for framing and routing information. This is crucial for transmission over potentially slow or unreliable wireless links like telemetry radios. It also includes built-in mechanisms for detecting packet loss and ensuring message integrity checksums, making it very reliable.
Where is it used? Just telemetry?
Now, MAV-Link is used extensively not only for the wireless telemetry communication with the GCS, but also often as the primary communication protocol between the main flight computer, autopilot, and any onboard companion computers, like a Raspberry Pi or NVIDIA Jetson doing vision processing. It supports communication over various underlying links, serial ports, UART, UDP over Wi-Fi or Ethernet, XBee radio modems, even GSM modems for cellular communication.
Super versatile.
Very. And one of its strengths is its extensibility. The message set can be easily extended via XML protocol specification files. These XML definitions allow developers to define custom messages for their specific needs, and tools can automatically generate the necessary source code for encoding and decoding these messages in various programming languages like C++, Python, Java. This makes MAV-Link incredibly flexible and adaptable for diverse drone applications and integrating new sensors or capabilities.
That sounds like a really powerful and standardized way for all the different parts of the complex drone ecosystem to communicate seamlessly, whether it's onboard components talking to each other or the drone talking back to the ground station. And there's also something mentioned called aerial middleware, specifically MAVDCon. What problem does that try to solve?
Yes, aerial middleware like MEVCon represents another layer of software abstraction, often built on top of protocols like MAV-Link. MEVCon, specifically, is described as a robotics toolkit tailored for computer vision-controlled autonomous lightweight micro-aerial vehicles, MAVs.
Vision-controlled again.
Right. It specifically addresses the potential high latency issues that can arise when using more general-purpose robotics middleware, like the Robot Operating System, ROS, for real-time drone control, especially over constrained links like serial connections or USB between the autopilot and a companion computer.
How does it reduce latency?
A key feature highlighted is its use of something called Lightweight Communications and Marshalling, or LCM. LCM is claimed to offer lower latency and high robustness compared to ROS's standard communication mechanisms, partly because it typically avoids a central master or server process for message routing. This eliminates a potential single point of failure and reduces communication overhead.
Okay, optimized for drone communication needs. What about handling images? That seems data intensive.
Exactly. MEVCon mentioned as providing a high-level API for a shared, memory-based image hub on the onboard companion computer. This allows camera images to be efficiently shared between multiple different software processes, for example, the camera driver, the object detection algorithm, a logging process, with minimal data copying and overhead. It can also provide bridges to allow communication with standard ROS nodes if needed, offering flexibility.
So it's about making sure data, especially that critical high-bandwidth image data, flows quickly and reliably between the different software parts doing the visual processing and control. Crucial for vision-based autonomous tasks.
Precisely. Getting that image data processed and turned into control commands with minimal delay is key.
And finally, a crucial feature for any drone pilot, especially if they're trying to film something dynamically or fly in complex environments. First-person view.
First-person view, or FPV, is indeed a crucial safety and operational feature for many drone applications. It involves an onboard camera, usually mounted facing forward, providing a live video feed from the drone's perspective.
Like being in the cockpit.
Exactly. This video is transmitted wirelessly via dedicated FPV video transmitters and receivers to a display screen, or FPV goggles worn by the pilot. This enables the pilot to control the drone accurately even when it's flying far away, potentially beyond visual line of sight, BVLOS, allowing for much more precise maneuvers and better situational awareness for tasks like aerial filming or navigating tight spaces.
What frequency does FPV usually use?
FPV systems typically operate in the 5.8 GHz band to avoid interference with the 2.4 GHz RC control link. Key parameters for FPV systems are the transmission range, the video bandwidth and resolution quality, and crucially, the communication delay or latency. Low latency is vital for responsive control, especially in fast-paced FPV racing or freestyle flying.
Makes sense. You need to see where you're going in real time.
Absolutely.
This all ties back perfectly to our core mission for this hypothetical aerial filming UAV. Robust, autonomous tracking of a moving object like that mountain biker in a dynamic sporting environment. How does the drone actually achieve this visual control we've been hinting at? It's not just pointing a camera, it's seeing and reacting based on that vision.
The visual control process in such a UAV is quite sophisticated, building on many of the components we've discussed. First, it's really important to reiterate that multi-rotor UAVs, like quadcopters, are inherently aerodynamically unstable.
They want to fall out of the sky.
Pretty much. They require continuous high-frequency attitude and position control corrections from the autopilot's onboard inertial sensor module just to stay level and hold position. Without thousands of tiny adjustments per second from the autopilot reacting to sensor data, they'd simply tumble.
So the autopilot is already working incredibly hard just to keep the drone steady, even before it starts trying to track anything visually.
Yes, it's a constant battle against instability, requiring immense processing power just for basic stabilization. On top of this stabilization layer, the visual tracking function is added. The camera input is critical here. An onboard computer, perhaps that companion computer we mentioned?
The Raspberry Pi or Jetson?
Right. It receives a continuous stream of images from a connected camera, often a USB camera, for simplicity and bandwidth. This camera feed is essentially the drone's eye, providing the raw visual data of the scene.
And then it has to figure out what it's looking at in that video stream. How does it pick out the specific athlete from potentially a busy background with spectators or other distractions?
That's where the image processing algorithms come in, running on that companion computer. An advanced image processing algorithm analyzes these incoming images frame by frame to identify and locate the object of interest, our athlete, in this example.
That sounds computationally hard.
It is. This isn't trivial. It involves sophisticated computer vision techniques. Things like feature detection, object recognition models, maybe deep learning based, background subtraction, motion analysis, all working together to filter out noise, account for varying light conditions, handle partial occlusions, and reliably distinguish the target from its surroundings.
So it sees the athlete, maybe puts a bounding box around them in its internal processing. Then what? How does that visual information translate into actually controlling the drone's flight?
Once the algorithm successfully identifies and locates the object, it typically calculates the center of mass, or centroid, of the detected object within the image frame. The image coordinates, X and Y position, of this center of mass are then continuously calculated and passed, often via MA-BLINK, to the UAV's main attitude control system running on the autopilot.
So it tells the autopilot, the thing I'm supposed to follow is currently at this pixel location in my camera view.
Exactly. This target position information essentially acts as a command input to the autopilot's control loops. The autopilot then adjusts the drone's roll, pitch, yaw, and altitude to try and keep that target point centered or at a desired offset in the camera's field of view, effectively causing the drone to actively follow or track the desired object.
Wow.
It's literally using its vision sensor data to directly influence its flight path and keep its subject perfectly in frame, creating that seamless autonomous aerial filming experience. It becomes a self-piloting camera operator.
That's incredible. A closed loop where the drone sees, processes, and reacts to keep the target framed. Amazing. So we've taken this incredible journey from conceptualizing a complex system like a drone, blueprinting its circuits with schematics, painstakingly designing its physical PCB layout, understanding the critical manufacturing elements like controlled impedance, and then diving deep into the vital components that bring it all to life, from intelligent batteries and fast ESCs to sophisticated communication protocols and this amazing vision-based control. But even with the most meticulous design, things can, and inevitably do, go wrong sometimes.
Oh, absolutely. Murphy's Law applies strongly to electronics.
And that's where debugging and maintenance become absolutely essential for ensuring reliability, both during development and throughout the product's life.
Debugging and troubleshooting are truly indispensable skills for any electronic circuit designer or technician. Glitches, bugs, failures, they can occur in both passive elements, like resistors drifting out of tolerance, capacitors failing short or open, inductors breaking.
The simple parts.
Right, and also in active elements, like transistors burning out, op-amps oscillating unexpectedly, or integrated circuits having internal faults or firmware bugs. Knowing how to systematically identify and fix these issues is paramount to getting anything complex working reliably. It's like being a detective for misbehaving electrons.
Undetected for electrons, I like that. So where do you even start when something goes wrong? Your drone isn't behaving, a circuit isn't working. Our sources give us 7 key techniques to debug an electronic circuit. First up, the simplest but often surprisingly effective, visual inspection.
Always start with a thorough visual inspection of the circuit board. Get good lighting, maybe use a magnifying glass or even a microscope if you have one.
What are you looking for?
Compare the physical circuit to your circuit diagram or assembly drawings. Meticulously check if all components seem to be in the right place and orientation. Look for obvious signs of damaged, burnt, or cracked components, scorch marks on the PCB. Check for loose connections, unsoldered pins, or very commonly poorly connected or shorted solder joints, little bridges of solder where they shouldn't be.
The simple stuff first.
Exactly. It's surprising how many issues can be resolved just by looking closely and finding a bad solder joint or component put in backwards. Sometimes the simplest solution is right there in front of you, hiding in plain sight.
It's like checking if it's plugged in before you assume the whole thing is broken. What's next if nothing obvious jumps out visually?
Second, check the power supply requirements. Is the circuit actually getting the power it needs? Ensure the power supply you're providing is sufficient for the load and delivering the correct voltage and current levels specified in the design.
How do you check?
Use a multimeter to measure the voltage at various key points on the board, at the input connector, after voltage regulators, at the power pins of major ICs. Abnormal readings too low, too high, or 0 volts where there should be voltage can immediately indicate a power supply issue, maybe a faulty regulator IC, or perhaps a short circuit somewhere on the board that's dragging the voltage down. If the power foundation isn't solid, nothing else downstream will work correctly.
Good point. Power first. Then you start looking at the components themselves. You'd probably start with the simpler ones, the passive ones, right?
Exactly. Third, examine passive elements. These components, resistors, capacitors, inductors, operate without needing external power themselves to function, though they are part of the powered circuit, of course. You can often evaluate them, sometimes even in circuit or by desoldering one end using a multimeter or an LCR meter.
LCR for inductance, capacitance, resistance.
Right. Measure the resistance, capacitance, or inductance. A continuity tester on the multimeter is also useful to verify the absence of short circuits where there shouldn't be one, or open circuits, broken connections, where there should be continuity. Compare your measurements to the values specified on the schematic or the component markings or data sheets. If you find a discrepancy, the component might be faulty, or the connections to it might be bad.
Okay, check the passives. What about the active elements, the transistors, ICs, things that do need power to operate? They seem harder to test.
They can be trickier. Fourth, examine active elements. For components like transistors, diodes, op-amps, and integrated circuits, which require external power to function, you typically need to test them under power. Use a multimeter, or even better, an oscilloscope, to measure their input and output voltages and currents while the circuit is operating, or supposed to be.
Look at the signals going in and out.
Exactly. See if they match what you expect based on the design or the component's datasheet. For digital signals, a logic probe, or a more powerful logic analyzer, can be invaluable for seeing the sequences of ones and zeros, checking timing, and verifying communication protocols. Compare the observed behavior to the expected behavior. Look for issues like incorrect biasing on transistors, op-amps stuck at their supply rails, missing clock signals, or data lines that are stuck high or low. If a component seems faulty, you might need to replace it.
I can imagine prototyping tools are a lifesaver during development for this kind of thing, letting you test parts of the circuit in a more controlled, accessible environment before it's all packed onto a dense PCB.
Absolutely. Fifth, using breadboards and prototype boards. These are invaluable diagnostic and development tools. Solderless breadboards with their grid of holes and internal spring contacts facilitate the effortless insertion and removal of through-hole components. They allow you to quickly build and test small circuit sections or ideas from your main design without any soldering.
Quick experiments.
Right. And prototype boards, like strip board or perf board, which have copper traces and pads for soldering, enable you to build and debug a more permanent version of your circuit, still with the capability for relatively quick design changes, cutting traces, adding jumper wires, before committing to the expense and delay of a full custom PCB manufacturing run. They let you experiment and iterate without risking your final expensive hardware.
And what about before you even touch any physical hardware at all? Is there a way to find potential issues purely in the design phase, on the computer?
Definitely. That's where simulation software, our sixth technique, really shines. Tools like SPICE-I, simulation program with integrated circuit emphasis, which is often integrated into EDE software like Altium, or standalone tools like Proteus, Multisim from National Instruments, allow you to build and simulate your circuit entirely on a PC.
Virtual testing.
Exactly. This eliminates any power hazards or the need for physical components during the initial design verification. These simulators use sophisticated mathematical models and algorithms to simulate the behavior of your circuit and its components over time or frequency. You can perform virtual measurements, see waveforms on a virtual oscilloscope, analyze voltages and currents, monitor or control variables with software commands, set breakpoints all before ordering parts or building anything physical.
Catching problems super early.
It saves immense time and resources by catching fundamental design flaws or predicting potential issues early in the process.
And finally, the often overlooked but incredibly important hero of debugging: documentation. It sounds tedious, but I imagine it's invaluable later on.
Seventh, and critically important, maintaining debug documentation and notes. This is crucial for tracking your progress and for future reference and efficiency. You must meticulously record every step you take during debugging, every measurement you make, every hypothesis you test, and all your findings and observations.
Keep a logbook.
Essentially, yes. This documentation not only aids in tracking progress during the current, often frustrating debugging session, helping you avoid repeating steps or going in circles, but it also serves as an incredibly valuable guide for future troubleshooting if a similar problem arises later, or if someone else needs to understand or repair the circuit. It builds a knowledge base that is invaluable for engineers and future projects, saving significant time and effort in the long run. Don't rely on memory alone.
Great advice. So once you've debugged the component and circuit level, the PCB design software itself has powerful automated checks built in to help prevent common layout errors before you even get to manufacturing. These are called design rule checks, or DRCs. It's like having a digital guardian angel watching over your layout.
Yes, exactly. Advanced PCB design software like Expedition or Altium Designer incorporates comprehensive design rule checks, DRC. These rules are predefined based on manufacturing capabilities, like minimum trace width, minimum spacing, and electrical requirements, like clearance between nets, signal integrity rules. The software automatically runs these checks to verify that your physical layout adheres to all these constraints.
What kind of errors does it catch?
All sorts. Things like traces being too close together, potentially causing shorts during etching, vias being too close to pads, components physically overlapping, signal traces crossing over plane splits without stitching, violations of controlled impedance rules, unconnected nets, incomplete routes, and many others. It's a critical automated verification step before sending the design files to a manufacturer.
But I've heard you can sometimes deliberately check off or temporarily disable certain DRCs while you're working, which sounds incredibly risky. Why would anyone do that? Is it ever justified?
It's a, let's say, controversial feature, and generally something to be avoided if possible. Disabling DRCs, or checking off specific violations, allows designers to intentionally place elements in violation of the defined rules.
Why?
Maybe for a very specific temporary reason during development, like intentionally shorting two nets together for a test configuration, or needing to slightly violate a clearance rule in one extremely tight spot with careful consideration. However, it is generally ill-advised and should be used very sparingly and with extreme caution.
Because you might forget you did it.
Exactly.
Yeah.
Disabling DRCs can easily lead to critical manufacturing or functional errors if not meticulously managed and documented. The software will often warn you if you have DRCs disabled or violations ignored, and usually provides a way to run a full badge checker later to find all the violations you've introduced. But it's fundamentally like building something without adhering to the safety regulations risky.
So it's a use at your own extreme risk kind of feature for highly specific controlled situations, not for everyday layout. And where do you manage all these complex rules and settings and see the list of errors the DRC finds?
Many of these crucial settings, including which DRC rules are active, layer visibility settings, routing behaviors like push and shove, are managed within a central control panel, often called something like the editor control or design rules panel in the software. And importantly, the software provides a dedicated window or tool, often called a hazards explorer, violation report, or similar, which lists all the detected DRC errors.
A list of problems to face.
Precisely. It allows designers to systematically click through each violation, see it highlighted on the board layout, understand the rule that was broken, and address it. This provides a clear, organized roadmap for resolving all the design rule violations before finalizing the design, much like working through a quality assurance checklist.
Okay. Now, beyond the critical controlled impedance rules we discussed, there are other PCB layout best practices that are vital for debugging ease later on, and just for overall reliability, making sure the physical board is as robust and manufacturable as the electrical design intends. Let's talk about some routing subtleties, like that gloss function you sometimes see. What does that do?
Ah, yes, the gloss function. This is a feature found in some EDA software, like Expedition. It attempts to automatically clean up and smooth out the traces you're routing, or existing traces, in real time. It tries to find the shortest, neatest path according to certain rules, maybe minimizing bends or optimizing spacing.
Sounds helpful.
It can be, sometimes. While intended to optimize routing and make it look neater, it can also be a bit temperamental. Sometimes it leads to unexpected trace deletions, or it aggressively reroutes segments in ways you didn't intend, or it creates fixed trace segments that then become difficult to move or modify manually. Many designers prefer to use gloss locally, which only affects the specific trace segment currently being routed, giving more predictable behavior. It's like having an overly helpful AI try to constantly organize your desk while you're working. Sometimes it's great, sometimes it just moves things you didn't want moved.
So it's supposed to make things neat, but can sometimes be a bit chaotic or fight against you. What about push and shove routing? That sounds aggressive. Is it helpful?
Push and shove routing is generally a fantastic and very helpful feature. As you're routing a new trace through a congested area, the software intelligently and automatically pushes existing traces and even via slightly out of the way to make room, while still maintaining the required clearance rules.
Like nudging things aside gently?
Exactly. This significantly speeds up the routing process in dense areas, as you don't have to manually reroute every single conflicting trace yourself. It just figures it out. It may occasionally fail or give up in highly complex scenarios where there's simply no valid path to shove things to, but most of the time it's incredibly useful for fitting everything into a tight space without hours of manual rework.
Okay, those are features of the tools. Beyond that, what are some fundamental best practices in the layout itself to prevent manufacturing problems or issues during assembly? Little things that can trip you up in production if you're not careful.
Good question. Firstly, think about pad entries for surface mount components. Traces should ideally connect to the pads of SMD components like resistors or capacitors, symmetrically if possible, for example, entering from both the left and right sides for a two-pad component or centered, rather than just connecting to one corner or edge.
Why does that matter?
It helps prevent issues during the reflow soldering process in automated assembly. If the trace entry is asymmetric, the surface tension of the molten solder might pull the component slightly off-center as it solidifies, leading to poor connections or even causing the component to stand up on one end, a defect called tombstoning. Symmetrical connections help balance those forces.
Ah, tombstoning. I've heard of that. What about sharp corners? I've often heard engineers talk about avoiding sharp 90-degree turns on circuit board traces. What's the hidden danger there at a microscopic level? Why are 90-degree bends considered a big no-no?
That's a subtle but very important detail rooted in the manufacturing process. Avoiding 90-degree bends in copper traces is strongly discouraged, especially in older or less precise manufacturing processes, but it's still good practice.
Why? What happens?
During the chemical etching process used to remove unwanted copper from the board layers, the etching solution can get trapped or concentrated in those sharp, acute inner corners of a 90-degree bend. This can lead to acid traps, where the copper in that corner gets over-etched, making the trace significantly thinner at the bend, or potentially even breaking it entirely.
So the corner gets eaten away more than the rest of the trace.
Exactly. This weakens the conductor at that critical point, potentially causing it to overheat and act like a fuse under high current, or simply fail unpredictably under normal operating conditions or mechanical stress. Instead, designers should always use 45-degree angles, or even better, smooth curves for trace bends to ensure consistent trace width and reliability throughout the path. It avoids creating those problematic sharp inner corners.
That's a fascinating insight. Acid traps make sense. What about the text and component outlines printed on the board, the silk screen layer? I imagine placement has to be precise there too.
Silkscreen placement is vital for assembly and debugging. Reference designators like R1 or C2, component polarity markings, and the component outlines themselves, printed on the silkscreen layer, should never be placed overlapping exposed copper pads or drill holes.
Why not?
If silkscreen ink gets printed onto a pad where a component needs to be soldered, it can interfere with solderability, leading to a weak or failed joint. If it's printed over a via hole, it might get drilled through or filled, rendering markings unreadable. Overlapping silkscreen can also obscure component markings needed for manual assembly or inspection. These silkscreen elements often need to be manually moved or adjusted in the layout software to ensure they are placed in clear areas, providing clarity for assembly, testing, and future maintenance without interfering with electrical connections.
So even with all these amazing automated software tools and DRCs, there's still a significant need for a final, careful human eye to review the whole layout, a final manual check.
Absolutely. The necessity of meticulous manual inspection of the fully routed board cannot be overstated. Automated tools are fantastic, but they can miss subtle issues or context-dependent problems. Designers must visually inspect the entire layout, checking for things like any remaining unrouted connections, rat's nest lines, unwanted accidental trace loops, ensuring correct pad entries, verifying proper silk screen placement, checking clearances in critical areas, and generally making sure that all design rules have been successfully applied and the layout looks sensible and manufacturable. This human oversight is the final, crucial quality control layer, catching potential issues that the automated checks might miss.
Trust but verify with your own eyes. And finally, what are polygons or copper pores, and what are they used for? I often see these large solid areas of copper filling up empty spaces on finished boards.
Polygons, also commonly called copper pores or fills, are used to fill in the remaining empty or unused areas on a PCB layer, typically a signal layer, with copper. This copper area is almost always connected to a specific electrical net, most commonly a ground net, GND.
Why fill the empty space with copper?
It serves multiple beneficial purposes. Firstly, it can help with heat dissipation for nearby components by providing a larger surface area to spread heat. Secondly, it provides electromagnetic shielding, helping to reduce noise and interference between different parts of the circuit or from external sources. Thirdly, and very importantly, connecting it to ground creates a large, low-impedance ground plane on that layer, which significantly improves signal integrity for nearby traces by providing a close, solid return path, and also helps stabilize the ground reference across the board.
So it's good for heat, noise, and signal quality. How do you create them?
In the software, designers draw a polygon shape around the area they want to fill on a specific layer. They then associate that polygon with a net, usually GND. Critically, they must define proper clearance distances between the polygon copper and other features like traces, pads, and vias, belonging to different nets to prevent accidental short circuits. The software then automatically fills the defined area, flowing around existing objects according to the specified clearance rules. This process is typically performed as one of the final steps after the main routing is complete, adding a final layer of electrical and thermal robustness to the design.
So this incredible drone journey, from concept to final board, seems to have come full circle. We've gone from an abstract idea for an aerial filming drone and its requirements, through creating the electrical blueprint with schematics, down to the intricate details of PCB layout using sophisticated EDA tools. We considered critical manufacturing aspects like controlled impedance and routing best practices. Then we delved into the vital components that bring these complex systems to life, from intelligent batteries with BMS and fast responsive ESCs to the sophisticated communication protocols like MAVEN Link that tie everything together, and even enabling advanced capabilities like vision-based control.
Right.
And woven throughout, we've highlighted the absolutely essential role of systematic debugging techniques and meticulous design practices like DRCs and manual inspection in ensuring the final product is actually reliable, a process that relies on both cutting-edge software tools and careful, experienced human attention to detail.
Indeed. All the design and operational considerations discussed today, from the individual mechanical and electrical subsystems like power and propulsion, to the complex control loops in the autopilot, the layered communication architecture using things like EVA Link and perhaps middleware like EVGoN, and the integration of advanced accessories like cameras enabling visual tracking via onboard computer vision, they all have to culminate and work together seamlessly in the functional high-performance UAV.
It's truly a marvel of interdisciplinary engineering.
It really is. Every single part, every line of code, every design choice, no matter how seemingly small, plays a crucial role in the overall capability and reliability of the system.
And the future work in UAV development sounds just as exciting, right? It feels like we're still just scratching the surface of what these autonomous systems can truly do as the technology continues to evolve.
Absolutely. The field is moving incredibly fast. Future work focuses on continuous improvement across the board. Things like even better, more robust image processing algorithms for smarter tracking and scene understanding, more advanced sensor fusion techniques, improved object avoidance implementations using LiDAR or vision for safer navigation in complex, cluttered environments, and the refinement of flight control processes using advanced techniques like model predictive control or optimal control for enhanced performance and efficiency. The capabilities of these autonomous systems are constantly expanding, really pushing the boundaries of what's possible.
What's truly fascinating here, looking back at our deep dive, is how every component, every software module, every careful design decision, and every debugging step we've discussed contributes synergistically to the overall intelligence and capability of these complex machines.
It's the integration that's key.
And it makes you realize, with the increasing complexity of our everyday technology all around us, understanding the fundamental principles of electronic design, communication, control, and debugging isn't just for electrical engineers anymore. It's becoming increasingly key to navigating, utilizing, and even innovating in our highly interconnected, technology-driven world.
That raises an important final thought, doesn't it? As you, our listeners, look around at the technology in your own lives, your car, your home appliances, the systems at your workplace, what other complex systems might benefit from a deeper dive, a conceptual unpacking, into their underlying electronic circuits and software?
Yeah, what's really going on inside?
And perhaps more broadly, how might these very same principles of systematic design, requirement analysis, careful integration, and methodical debugging apply to solving challenges in any complex system you encounter, even those far beyond the realm of electronics?
Something to ponder.
Definitely something to ponder. Think about that until next time, deep divers.